All right, I know I just introduced you to a lot of terminology: polynomial, standard form, degree, leading coefficient, leading term, constant term. So in example 2, I have a nice little question that's very concise, and I can test you over all of these concepts. So I've been known to put this on the test quite a bit when it comes test time for this material, okay? All you have to do, and we'll read the directions in just a second, is basically make up your own polynomial as long as it meets the criteria stated in the question. So in example 2, I want you to write a polynomial function in standard form of degree 7 with exactly 5 terms, including leading coefficient -36 and constant term 11. Okay, so let's try this. Okay, first of all, you know that the polynomial has to have 5 terms. Okay, so I'll kind of draw a little framework here for this. We're going to have 5 pieces, 1, 2, 3, 4, 5, to our polynomial. Okay, so we gotta fill in the blanks. Okay, so what do we know? Let's see. We know, let's see, that the constant term is 11. Okay, so constant term, remember, that's just the number at the end. Okay, and remember, you've got to write it in standard form, so the constant term has to be at the end. So we're going to have plus 11. Okay, so that's got to go there. Okay, what else do we know? We know that the degree is 7. Okay, so the highest power of x that you're going to see in the whole thing is the 7th power. So your polynomial is going to start with x to the 7th. Okay, again, standard form forces this piece to be the first term. Okay, the leading coefficient, which is the number in front of the highest power of x, is -36. So -36 has to go in front of the x to the 7th power, so they're going to be multiplied together. So your first term is going to be -36x times x to the 7th. And after that, that's kind of what is required, okay? And you still have to have 5 terms, so you can't leave these blank, so you're going to have to fill them in with something. But what's in blue here is required, okay? So the rest of the stuff I'm going to put in pink. This is what you're going to make up, okay? We've got to fill in the 3 middle terms here. And you can put pretty much anything you want as long as you go with descending powers of x, okay? So I'm just going to make up something, just, you know, minus 12x to the, I don't know, 4th plus 2x to the 3rd plus 5x, okay? That'll do it. You can put anything you want. Like I said, even though this is 7th power, okay, you don't have to go 6, 5, 4, 3, you know, you don't have to do that. It can be, as long as you have descending powers of x, you're good. You can use any coefficient, which means the numbers in front. You can use anything you want. The signs can be positive or negative. The only thing that is required is the stuff in blue. Your first term has to be -36x to the 7th, and your last term has to be the constant term, 11. Okay, so I'm going to put over here that the pink stuff make these terms up, and then the blue stuff is what's required by the problem. Okay. All right, so that's a nice little problem where I can test you on all the terminology. All right, so now that we know what a polynomial is and all the terminology associated with it, we're going to start concentrating on what does the graph of a polynomial look like, okay? And to be honest, you're going to find out in just a second, we've been dealing with polynomials the entire semester. We just didn't call them polynomials, okay? So there's going to be a lot of back work that we're going to do and work our way up to actually sketching the graph of a polynomial function. So right now we're going to concentrate on general shape of a polynomial, and that depends on the degree of the polynomial. Okay, so let's start off with the first bullet point here. It says the graph of a polynomial of degree 0 is a blank. Okay, so what does it look like? Well, we just saw a 0-degree polynomial a few minutes ago. Okay, so I'm going to go back up here. Okay, remember 2, this was our polynomial. It was a degree 0 polynomial, okay, because it didn't have an x with it. Okay, so let's just use that one. Okay, So basically, anytime you just have a number, if your function is a constant, just a number, that's a degree 0 polynomial, okay? So an example of a degree 0 polynomial is f of x equals 2, okay? Remember, polynomials are functions, so I'm just using function notation here. If we translate this, f of x is the same thing as y, okay? So what does the graph of y equals 2 look like, okay? Well, we've seen this before, okay? If it's y equals a number, it's a line, okay? And specifically, it is a horizontal line, okay? So remember, I'm just sketch a little graph of this over here, like really small graph, okay? So if these are my axes, x and y, okay? And then I want to know where y equals 2, okay, like that, okay? And then if I look at the horizontal line through this, okay, this is a function, and every point on this line is going to have a y coordinate of 2, okay? So this is the graph of the equation y equals 2, okay? Y equals means it's going to be a horizontal line if it's y equals a number, okay? All right, so this is the graph of this particular polynomial. So if you have degree 0, the graph is just going to be a horizontal line. Okay, so we did that back in 2.2 when we studied lines. We looked at the graphs of horizontal lines. Those are polynomials. They're just degree 0 polynomials. We know that now. Okay, so now let's bump it up a degree. Okay, the graph of a polynomial of degree 1. What does that look like? Okay, well, let's use our function notation. Let's make up something of degree 1. Okay, I don't know, I'm just using the first thing that comes to my mind. 2x minus 1. Okay, this is a polynomial. It is degree 1. This little piece is in standard form. The highest power of x is 1. Okay, and when you look at this, this is nothing more than y equals mx plus b, okay? We know that this is going to be a line as well, okay? Now, what is the difference between degree 1 and degree 0, okay? Because they're both lines. Well, because you're forced to have x to the first power in your equation, okay, you have to have this little piece, okay? So you're going to have the mx part, okay? So the difference here, this is a line with a non-zero slope, okay? So degree 1 is going to be a line with non-zero slope, okay? Because if you have 0 slope, then the x would go away and leave you with just a number, okay? So there you go. Degree 1 is a line with non-zero slope. Like, for example, this polynomial, this is a polynomial of degree 1, highest power of x is 1. It's a line with slope 2, y-intercept negative 1. Okay? Again, we've seen this before. We just didn't call it a polynomial. All right, next page. What does degree 2 look like? Okay, so again, if you're trying to figure out what the polynomial of degree 2 looks like, just make up something of degree 2. So use your f of x notation, okay? Degree 2 means the highest power of x is 2, so I'm just making something up. We might have f of x is equal to negative 2x squared plus 3x minus 4. I'm just making something up, okay? Highest power of x is 2, okay? You look at this, this is ax squared plus bx plus c. Okay, so degree 2 is a parabola, okay, and we've seen that before, okay? So all lines, all parabolas, they are polynomials, okay? So this section really concentrates on higher degree polynomials, meaning what happens if I have the highest power of x is the third power, the fourth power, fifth power, sixth power, so on, okay? We've spent so much time in this class already on polynomials of degree 0, and degree 1 and degree 2. Okay, we've looked at lines and we looked at parabolas extensively. So now we're going to really concentrate on those higher powers. Okay, so when we're talking about higher degrees, this means x cubed or higher. So the degree needs to be 3 or higher. Okay, because we really haven't looked too much at those. Okay, so that's what we're going to be concentrating on in this section. Okay, as far as the shape goes, it really depends on whether the degree is even or odd. Okay, so let's take a look at this. So it says for higher degrees, if the polynomial has an odd degree, its graph is what kind of shape, okay? Well, what you're going to do here is think about, I'm going to go up here. So if I'm thinking about an odd degree, think of the simplest odd degree polynomial we've seen in this class, okay? Back when we were doing the library of functions and we learned our parent functions for graphs, the simplest odd degree polynomial that we learned was x to the third power, okay? Highest power of x is 3, okay? That's an odd degree, okay? And you should remember, hopefully, what the graph of x cubed looks like. It was that long s, okay? So there you go, okay? So what this is going to tell you, okay, this is what you need to keep in the back of your mind, that x cubed, anytime you have an odd degree polynomial, it is going to look or resemble x cubed. It is going to be S-shaped, okay? Now remember, you could do transformations with this guy, okay? So you could reflect it. It might look like this, okay? But it's going to have some kind of S shape to it, okay? So I'm going to go ahead and write that down, okay? If a polynomial is of odd degree, its graph is going to be S-shaped, okay? And then if the polynomial has an even degree, well, we're going to do a similar kind of thing, okay? When we went back to that, think back to that library of functions, the simplest even degree polynomial we know is x squared. Okay, so we know what x squared looks like. Okay, x squared is that very basic parabola that does this. Okay, so anything that's even is going to have a similar shape to x squared. Okay, so this is a U shape. Okay, now if you bump up the degree with even polynomials, your graph might get a little more complex. Okay, for example, as soon as you hit x to the fourth, as soon as you hit to x to the fourth power, fourth degree polynomial, you start getting into this kind of shape where it looks like a W, okay? And you could, of course, reflect that. So you might get an elm, okay? So when you're dealing with an even degree, okay, I'm going to put that you could have a U shape, which would just be a parabola, or if it's higher than the second power, like if it's x to the fourth, x to the sixth, x to the eighth, you might see a W shape. You might see something elm shaped, okay? But that's generally what they're going to look like, okay? All right, so other attributes of polynomial functions, okay? It says the graph of a polynomial function is a curve that is always blank, meaning the graph contains no sharp corners or cusps, and blank, meaning it has no gaps or holes and can be drawn without lifting your pencil from the paper, okay? So there's two things that go in the blank, okay? Two properties of polynomial functions, okay? One of these ideas we've seen before, okay? The second blank, if you have a function that has no gaps or holes and can be drawn without lifting your pencil from the paper, we've spoken about this word before. It's continuous, okay? Continuous means you can draw it without picking up your pencil, okay? So if you have a polynomial function, it is always, always, always going to be continuous, meaning you can draw it without picking up your pencil, okay? Something that we've seen in the past that was not a polynomial were a lot of piecewise functions are not continuous, okay? That's when we first heard this term continuous in this class. A lot of times when you have a piecewise function, you start with one rule and then you have to lift your pencil to go draw the second rule out, okay? And so then that devoids the continuity there, okay? But polynomials will always be continuous. You can draw them without picking up your pencil, okay? So many piecewise functions are not polynomials because they are not continuous everywhere, okay? The other term that goes in the first blank is something we haven't heard before, and the word is smooth, okay? So polynomials are always smooth and continuous. Their graphs are, okay? So what smooth means, the graph contains no sharp corners or cusps, okay? So sharp corner, we've seen that before, okay? Something that has a sharp corner is absolute value, okay? So when I first brought up the definition of a polynomial to you, I said you wouldn't see absolute value, in a polynomial function, and this is why, because absolute value is not smooth. It has a sharp corner in it, okay? So that prohibits it from being a polynomial, okay? What a cusp is something like that looks like this. Like you might have a hump and then you come to kind of this corner looking thing and then you go back up, okay? So this right here is a cusp, okay? So the sharp corner, which is absolute value, okay, and the cusp, okay, those are features you will not see in the graph of a polynomial function, okay? Every polynomial function has to be smooth and continuous, okay? All right, so now what I'm going to do to illustrate these points, I have two graphs here, and I'm just going to draw some random things here to show you what a polynomial looks like versus something that is not a polynomial, okay? So polynomial, it's got to be smooth and continuous. So when I draw it, I'm not going to lift my pencil, okay? And it's got to be smooth. No sharp corners, no cusps. Everything's got to be flowy, flowy. So I might get something that looks like this, okay? This is a polynomial function, okay? Something that is not a polynomial, okay? I mentioned it to you a few minutes ago, piecewise, okay? Let me just draw some random piecewise function here, okay? This is clearly not continuous. I have to, pick up my pencil to draw this, okay? So that's not a polynomial. Okay, again, something else you could draw if I asked you to draw something that wasn't a polynomial. If you saw a sharp corner, okay, if you drew absolute value, that's not a polynomial, okay? But keep in mind, and you are going to have to sketch little graphs, little rough sketches of polynomials. When you draw your polynomial, must be continuous. You have to draw it without picking up your pencil, okay? And everything has to be rounded out, no sharp corners, no cusps, and it's very flowy, okay? All right, so now we are going to get into the specifics about how you actually graph a polynomial function of higher degree.